On the morning of February 23, 1945, Oberingenieur Klaus Richter stood in a frozen field 30 kilometers west of the Oder River, staring at something that should not have existed. Before him sat a captured American M4 Sherman tank, its olive drab paint scarred by artillery fragments, one track blown off by a Panzerfaust hit that had finally stopped it after 3 days of pursuit. Richter was not a soldier. He was a senior design engineer from the Waffenamt, Germany's weapons development office, assigned to the Eastern Front to investigate why German Panther tanks kept losing engagements they should have won. He had spent 9 years designing armored vehicles. He understood armor thickness, gun penetration, automotive engineering. He knew what made a tank superior on paper. The Panther OSFG was superior on paper. It weighed 45 tons, compared to the Sherman's 30 tons. Its frontal armor measured 80 millimeters, sloped at 55 degrees, effectively 140 millimeters against penetration. The Sherman's frontal armor was 51 millimeters at 56 degrees, effectively 90 millimeters. The Panther's 75mm calibre C-42 L-70 gun could penetrate 138 millimeters of armor at 1,000 meters. The Sherman's 75mm M3 gun could penetrate 68 millimeters at the same range. Every technical specification favored the Panther. Yet, Richter had spent the previous week interviewing Panzer crews who reported the same impossible story. Sherman tanks were faster in combat. They maneuvered better. They could reverse out of ambush positions before Panthers could traverse their turrets. They appeared in places Panthers could not reach. They crossed terrain Panthers avoided. The crews were not lying. Richter had checked after-action reports from 17 separate engagements. In 12 of them, American Sherman units had successfully withdrawn from combat against superior German armor. In 8 engagements, Shermans had maneuvered onto Panther flanks, despite the Panthers having better engines and higher road speeds. Something was fundamentally wrong with the German understanding of American tank design. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Richter ordered the captured Sherman towed to a Wehrmacht repair depot at Kustrin. He wanted the tank disassembled completely, engine removed, transmission torn down, suspension examined, every component measured and analyzed. He'd done this before with captured Soviet T-34 tanks in 1942. That investigation had revealed why T-34s were outperforming German armor, despite inferior optics and crew training. The answer had been sloped armor and a diesel engine that kept running in winter conditions that froze German gasoline engines solid. The Sherman investigation would reveal something more fundamental, something that challenged everything German engineers believed about proper tank design. The disassembly began on February 25th. Richter brought 3 senior engineers from the Waffenamt, 2 automotive specialists from Porsche, and 4 Panzer officers who had commanded Panthers in combat. They needed military input to understand what these technical findings meant in actual fighting. The first surprise came when they removed the engine compartment access panels. The Sherman's Continental R975 radial aircraft engine sat in a compartment designed for easy removal. 4 men could unbolt the engine mounts, disconnect fuel lines and electrical systems, and lift the entire engine out using a simple hoist in under 4 hours. One of the Porsche engineers, a man named Heinrich Wald, who had worked on the Tiger's Maybach HL230 engine, physically stepped back from the Sherman. He had spent 2 years refining the Panther's engine installation. Removing a Panther's Maybach HL230 engine in the field required a specialized recovery vehicle, a crane, and 12 hours of work by trained mechanics. The engine had to be lifted vertically through a relatively small access point. Fuel lines, coolant systems, and electrical connections were difficult to reach. Reassembly required precise alignment of drive shafts and adjustment of dozens of connection points. The Sherman's engine lifted straight up. Everything was accessible. Fuel lines had quick disconnect fittings. The electrical system used standardized military connectors that could be unplugged by hand. The transmission could be accessed separately without removing the engine. Wald said it was impossible to achieve this level of serviceability in a combat vehicle. German doctrine held that field maintenance meant minor repairs. Engine replacement happened at depot facilities far behind the lines. Richter pointed out that American doctrine appeared to be different. If Sherman crews could replace an engine in 4 hours at the front line, they could get damaged tanks back into action in 1 day instead of 1 week. The operational implications were staggering. The second surprise came from the transmission. The Sherman used a synchromesh transmission with 5 forward gears and 1 reverse gear. The gear ratios were carefully selected to provide smooth acceleration and a reverse speed equal to roughly 40% of forward speed. Panther tanks used a 7 forward gear transmission with a single reverse gear. The reverse gear was not synchronized and provided a maximum speed of 4 kilometers per hour, about 2.5 miles per hour. Panthers could sprint forward at 46 kilometers per hour on roads. They could barely crawl backward. One of the Panzer officers, a Hauptmann who had commanded a Panther company in Normandy, explained what this meant in combat. When a Panther fired from a defensive position and needed to withdraw before return fire arrived, it had 2 options: reverse, slowly exposing its thin rear armor to enemy guns, or turn around, which took 20 to 30 seconds and also exposed thinner side armor. When a Sherman fired and needed to withdraw, it could reverse at 12 kilometers per hour, 7.5 miles per hour, while keeping its frontal armor toward the enemy. The Sherman could back into cover in the time it took a Panther to begin its turn. The Hauptmann said he had lost 7 Panthers in Normandy to this exact tactical disadvantage. His tanks would fire, score hits, then attempt to reverse into cover. American tank destroyers or Shermans would return fire during the slow withdrawal. 3 Panthers were penetrated through the side armor while attempting to turn around. 4 were penetrated through the thin rear armor while reversing slowly. He had reported this deficiency in July 1944. His report had been filed and ignored. German doctrine held that tanks should not reverse from combat. They should press forward. Retreat was a symptom of poor morale, not a tactical necessity. The American doctrine appeared to assume that tanks would need to withdraw regularly. The Sherman was designed for tactical flexibility, not doctrinal purity. The third surprise came from the suspension system. The Sherman used a vertical volute spring suspension, or VVSS, with 3 bogies per side, each carrying 2 road wheels. The entire suspension assembly could be unbolted and replaced as a unit. Individual road wheels could be changed in under an hour. The springs were standardized, commercial truck springs, readily available and easy to manufacture. The Panther used a torsion bar suspension with 8 overlapping road wheels per side. The system provided excellent cross-country performance and a smooth ride. It also created maintenance nightmares. The road wheels overlapped, meaning that to replace an inner wheel, crews had to remove up to 4 outer wheels first. Torsion bars ran across the hull floor, making them difficult to access and impossible to replace without specialized tools. In winter, mud and snow packed between the overlapping wheels and froze solid. Panther crews spent hours every morning chipping ice from between road wheels just to move their tanks. If one road wheel was damaged, the ice had to be cleared from multiple wheels before repairs could begin. The Sherman's suspension was crude by German engineering standards. It was also practical. Road wheels did not overlap. Ice could not pack between them. Damaged components could be replaced quickly with simple tools. Wald calculated that a Sherman crew could replace a damaged road wheel assembly in 90 minutes using a jack, a wrench, and 3 men. A Panther crew needed 4 hours, specialized tools, and often had to clear ice from multiple wheels before beginning work. Richter had the crews measure ground pressure. The Sherman, weighing 30 tons and riding on relatively wide tracks, exerted a ground pressure of 13 pounds per square inch. The Panther, weighing 45 tons despite its wider tracks, exerted 14.8 pounds per square inch. The Sherman had better ground pressure despite being designed years earlier. It could cross soft ground that bogged Panthers. The overlapping wheel design that gave Panthers superior ride quality also made them heavier and increased ground pressure. The fourth surprise came from the fuel system. The Sherman carried 175 gallons of gasoline in armored fuel tanks located low in the hull. The fuel system included a primer pump that allowed crews to manually pressurize fuel lines if the electric pump failed. Fuel filters were accessible from inside the crew compartment. The Panther carried 190 gallons of gasoline in multiple tanks. The fuel system relied on an electric pump with no manual backup. Fuel filters were located in the engine compartment, inaccessible while the engine was running. If the fuel pump failed, the Panther was immobile until repairs could be made. American tanks could limp home on manual fuel pressure if their pumps failed. German tanks could not. The fifth surprise was the most significant. It came from measuring the Sherman's turret traverse mechanism. The Sherman's turret used a hydraulic traverse system powered by the main engine. The gunner could rotate the turret 360 degrees in 15 seconds at maximum speed. Fine adjustments could be made with a manual hand crank that gave precise control for aiming. The system worked identically whether the tank was stationary or moving, on flat ground or tilted. The Panther's turret used a hydraulic traverse system that was theoretically faster, capable of a full rotation in under 10 seconds. But the system's performance degraded significantly when the tank was not level on sloped ground. With the tank tilted more than 5 degrees, hydraulic pressure dropped and traverse speed decreased by up to 60%. Panther crews had reported this problem repeatedly when fighting on slopes or uneven terrain, which described most combat conditions in France and Western Russia. Their turret traverse became sluggish. Gunners switched to manual traverse, which required tremendous physical effort to rotate a turret weighing over 6 tons. The Sherman's hydraulic system maintained constant pressure regardless of hull angle. It was not faster than the Panther's system under ideal conditions, but ideal conditions rarely existed in combat. Under realistic conditions, the Sherman could traverse faster. Richter had found the answer. The Sherman outmaneuvered Panthers not because of superior speed or more powerful engines, but because every system in the tank was designed for battlefield reliability rather than engineering excellence. German tanks were designed by engineers who valued technical sophistication. American tanks were designed by engineers who valued maintainability and tactical flexibility. The Panther was a better tank in static trials. The Sherman was a better tank in combat. The implications extended beyond individual technical choices. They reflected fundamentally different design philosophies. German armor doctrine emphasized the decisive engagement, the knockout blow. Panthers were designed to dominate in direct confrontations with enemy armor. Thick frontal armor deflected enemy shells. The powerful long gun destroyed enemies at range. Speed allowed Panthers to choose when and where to fight. This doctrine assumed that superior German crews using superior German tanks would win battles through technical excellence and fighting spirit. The design reflected that assumption. Complex systems provided maximum performance. Maintenance happened at rear depots. Battlefield repairs were not prioritized because properly employed Panthers should not need them. American armor doctrine emphasized operational tempo and numerical superiority. Shermans were designed to be deployed in large numbers, maintained in the field, and kept in action through rapid repairs. Individual tank performance was secondary to fleet availability. A Sherman that could be repaired in 4 hours and returned to combat was more valuable than a Panther that required 12 hours of depot-level maintenance. The German design philosophy created tanks that were magnificent when they worked. The American design philosophy created tanks that kept working. Richter compiled his findings into a technical report dated March 8, 1945. The report was 17 pages of detailed analysis with photographs, measurements, and comparative tables. He sent copies to the Waffenamt, to Porsche, to Daimler-Benz, and to the Panzer Inspectorate. The report documented something German armor designers had refused to acknowledge. American engineers understood armored warfare better than Germans did. Not the theoretical warfare described in doctrine manuals, but the actual warfare fought in mud, snow, mechanical breakdowns, and constant retreats, where keeping tanks operational mattered more than maximum performance. The report arrived too late to matter. Germany was collapsing. Soviet armies were crossing the Oder. American armies were across the Rhine. There would be no new tank designs, no improved Panthers incorporating American maintenance concepts. The war would be over in 8 weeks. But Richter's report explained something that had puzzled German commanders since Normandy. Why did American armored divisions maintain higher operational readiness rates than German divisions despite suffering heavier losses? The answer was in the engineering. Sherman tanks that threw tracks could be repaired in 2 hours by their crews. Panthers that threw tracks needed recovery vehicles and 4 hours of work. Sherman tanks with engine problems could swap engines in a field workshop in 4 hours. Panthers with engine problems went to depot facilities for 12-hour repairs. Sherman tanks with damaged suspension could replace entire bogie assemblies in 90 minutes. Panthers needed 4 hours to change a single inner road wheel. American armored divisions kept 70 to 80% of their tanks operational at any given time. German Panzer divisions rarely maintained 50% operational readiness. The gap was not from American tanks being more reliable. Shermans broke down regularly. The gap came from American tanks being designed for rapid field repair. A Sherman battalion with 30 tanks would typically have 24 operational, 6 under repair. The 6 under repair would be fixed and returned to service within 24 hours. A Panther battalion with 30 tanks would have 15 operational, 15 awaiting repair or spare parts. The 15 awaiting repair might take 3 days to fix because they needed specialized tools, depot facilities, or parts that were not available at the front. Over a 2-week period, the Sherman battalion maintained consistent strength. Tanks broke, were repaired quickly, and returned to combat. The Panther battalion's strength declined as damaged tanks accumulated faster than depot facilities could repair them. By February 1945, this pattern had repeated itself across every front. German Panzer divisions reported chronic vehicle shortages, not because Panthers were being destroyed in combat, though many were, but because damaged Panthers were piling up in repair queues that stretched for weeks. This 6th SS Panzer Army that launched the Ardennes offensive in December 1944 started with over 400 Panthers and King Tigers. Within 2 weeks, fewer than 100 were operational. The Americans had destroyed some. Mechanical failures had disabled most. The German recovery and repair system could not keep pace with the breakdown rate. American armored divisions in the same offensive started with roughly 300 Sherman tanks per division. After 2 weeks of heavy combat, they still fielded 220 to 240 operational tanks per division. Some had been destroyed. Many had been damaged and repaired in field workshops using replacement engines, transmissions, and suspension units that arrived by truck within 24 hours. The German logistics system was designed for a short victorious war. Damaged tanks went to factory depots for expert repair. Replacement parts were manufactured to precise specifications. Everything was controlled, organized, efficient. When the war became a grinding attrition struggle, the system collapsed. Depots were bombed, factories were destroyed, replacement parts stopped arriving. Specialized repair facilities were overrun by advancing enemies. The American logistics system was designed for industrial-scale warfare. Damaged tanks were repaired at the front using standardized parts manufactured by multiple factories. If one factory was destroyed, others increased production. If parts did not arrive, mechanics improvised using commercial components. Nothing required specialized facilities. Everything could be fixed with basic tools and semi-skilled labor. Richter's report included a section analyzing American spare parts logistics. He had found documentation on a captured Sherman showing it had received 3 replacement engines during its service life. The first engine failed after 600 hours of operation. It was replaced in 4 hours at a field maintenance facility. The second engine failed after 400 hours. It was replaced in 5 hours. The third engine was still running when the tank was captured. 3 engine replacements in combat conditions. The tank remained operational throughout. No Panther could match that record because Panther engine replacement required depot facilities that might be hundreds of kilometers behind the lines. American maintenance doctrine assumed components would fail and designed replacement procedures accordingly. German maintenance doctrine assumed components should not fail and treated failures as anomalies requiring expert intervention. Both doctrines reflected their nation's industrial capabilities. Germany could produce sophisticated components but could not produce them in large quantities. Therefore, German doctrine emphasized careful maintenance to extend component life. Replacement was expensive, time-consuming, and required skilled technicians. America could produce standardized components in enormous quantities. Therefore, American doctrine emphasized rapid replacement over careful maintenance. Why spend 8 hours rebuilding a carburetor when a new one could be installed in 30 minutes? The Sherman's Continental R975 radial engine was not designed for tanks. It was a commercial aircraft engine adapted for ground use. It was mass-produced by multiple manufacturers. It was designed to be installed and removed quickly for routine maintenance. When Ford, Chrysler, and General Motors began producing Sherman tanks, they already had experience manufacturing and supporting the R975 engine because it was used in civilian aircraft. The Panthers Maybach HL-230 engine was designed specifically for tanks. It was a masterpiece of automotive engineering, producing 700 horsepower from a compact package. It was manufactured exclusively by Maybach, a specialty firm that produced limited quantities. Each engine required extensive hand-fitting during assembly. No other manufacturer could produce them without years of tooling development. When Allied bombing destroyed Maybach's factories in 1944, Panther production slowed because replacement engines were not available. When bombing destroyed American engine factories, Sherman production continued because multiple factories produced interchangeable engines. Richter calculated that American industry produced approximately 47,000 Sherman tanks during the war. Each tank required one engine. Plus, the American Army stocked replacement engines at a ratio of 1 spare for every 2 tanks in service. That meant American industry manufactured approximately 70,000 R975 engines or equivalents. German industry produced approximately 6,000 Panthers. Each required one Maybach HL-230 engine. Spare engine production was limited because Maybach's capacity was consumed building engines for new tanks. Richter estimated Germany produced perhaps 7,000 HL-230 engines total. The ratio was 10 to 1. 10 American tank engines for every German tank engine. That ratio appeared throughout the supply chain. American industry produced tank tracks, road wheels, transmissions, gun barrels, optical sights, and every other component at ratios between 8 to 1 and 15 to 1 compared to German production. Individual German components were often superior. The Panther's gun sight was more precise than the Sherman's. The Panther's armor was better designed. The Panther's gun was more powerful. But superiority in individual components could not overcome inferiority in industrial capacity. A Sherman with a damaged gun sight could be repaired in 2 hours by installing a replacement sight pulled from depot stocks. A Panther with a damaged gun sight waited days or weeks for a replacement to arrive from Germany, if one arrived at all. By 1945, many Panthers were operating with degraded capabilities, missing optical equipment, damaged road wheels that could not be replaced, engine governors disconnected because replacement parts were unavailable, machine guns removed to save weight when springs wore out. The tanks were still formidable, but they were deteriorating as the spare parts pipeline dried up. Shermans maintained consistent capability because spare parts never stopped flowing. American factories produced components faster than combat could destroy them. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Richter's report included interviews with Panther crews about their combat experiences against Shermans. The interviews revealed tactical patterns that confirmed the technical findings. Panther crews reported that American armor rarely engaged in direct frontal assaults against prepared German positions. Instead, Sherman units maneuvered onto flanks, forced Panthers to reposition, then withdrew before German tanks could close to effective range. The tactic worked because Shermans could reverse quickly. They would appear, fire several shots, then back into cover before Panthers could traverse their turrets and return fire. If Panthers advanced to pursue, Shermans would appear on a different flank and repeat the process. German crews called it swarm tactics. Individual Shermans were not threatening. A platoon of Shermans maneuvering aggressively while supporting each other was extremely dangerous. The Shermans used their superior reverse speed and faster sustained turret traverse to avoid direct confrontations while wearing down German tanks through mobility. One Panther commander, Hauptmann Ernst Weber, described an engagement near Aachen in October 1944. His platoon of 4 Panthers engaged an American company of 14 Shermans in rolling farmland. The Panthers had superior positions on a hillside overlooking a river valley. The Shermans should have been massacred attempting to cross open ground. Instead, the Shermans maneuvered along the river using terrain for cover. They appeared briefly, fired, then reversed into defilade before the Panthers could respond. The Americans used smoke grenades to obscure their movements. When Panthers repositioned to engage, Shermans appeared from different directions. The engagement lasted 40 minutes. The Panthers destroyed 3 Shermans. The Americans withdrew intact with the remaining 11 tanks. Weber called it a draw, but Richter recognized it as an American victory. The Shermans had forced the Panthers to remain defensive, prevented them from controlling the river crossing, and withdrawn in good order with minimal losses. The engagement demonstrated everything wrong with German tactical doctrine. Panthers were designed for decisive battles. Shermans were designed for sustained operations. The Americans avoided decisive battles and won through operational persistence. Weber's account included details that revealed deeper problems with German armor employment. His Panthers had fired 47 rounds of 75mm ammunition during the engagement. They had achieved 3 kills, a hit rate of roughly 6%. The low hit rate resulted partly from the Shermans' constant movement and use of smoke, but also from the Panthers' turret traverse problems. Weber reported that 2 of his Panthers had been positioned on sloped ground. When Shermans appeared on their flanks, the gunners attempted to traverse their turrets quickly. The hydraulic traverse systems, fighting against gravity on the sloped hull, moved sluggishly. Both gunners switched to manual traverse, but rotating the heavy turret by hand while the tank was tilted required tremendous effort. By the time the guns were aligned, the Shermans had reversed into cover. The 2 Panthers on level ground had better traverse performance, but they faced a different problem. When they fired and recoiled, the entire tank rocked backward on its suspension. The rocking motion took 3 to 4 seconds to settle. During that time, the gunner's sight picture was unstable. The Americans, apparently aware of this characteristic, used the post-firing interval to reverse into cover before the Panther gunners could fire again. Sherman tanks, being lighter and having softer suspension, also rocked after firing, but their faster reverse speed meant they could begin moving before the rocking settled. The combination of immediate reversal and protective frontal armor gave Sherman crews a crucial 3 to 4 seconds to escape before return fire arrived. Weber also noted that his Panthers had experienced mechanical problems during the engagement. One tank's final drive made grinding noises that suggested bearing failure. The driver reported the problem, but there was no possibility of repair during combat. The tank continued operating, knowing the final drive might fail catastrophically at any moment. It did not fail during that engagement, but 2 days later, the final drive seized completely. The tank was towed to a depot facility and was still awaiting repair when American forces overran the depot 3 weeks later. Another Panther in Weber's platoon had a faulty fuel pump that caused occasional engine stalling. The driver had learned to restart the engine quickly, but during the engagement, the tank stalled twice at critical moments. Both times, the driver restarted within 30 seconds, but those 30 seconds of immobility left the tank vulnerable. The crew was fortunate that American fire did not hit them during the stalls. Weber's after-action report noted these mechanical problems and requested priority maintenance. He received a response 3 days later, stating that no maintenance slots were available for 2 weeks. His platoon was expected to continue operations with degraded equipment. This was normal by late 1944. German maintenance capacity could not keep pace with mechanical wear and combat damage. Richter compared Weber's experience with maintenance records from captured American units. A typical American tank battalion had an organic maintenance company with 43 mechanics, specialized tools, and stockpiles of common replacement parts. The maintenance company could perform engine replacements, transmission overhauls, suspension repairs, and electrical system troubleshooting without external support. When a Sherman developed mechanical problems, it was pulled from the line for immediate repair. If repairs could be completed in under 8 hours, the tank returned to its platoon the same day. If repairs required more time, a replacement Sherman was issued from the battalion reserve pool. American tank battalions maintained a reserve of 5 to 8 extra tanks, specifically to ensure that combat companies stayed at full strength while damaged tanks were being repaired. German Panzer battalions had no such reserves. There were no extra Panthers. Every tank was needed in combat. Mechanical problems were tolerated until they became catastrophic failures. Then the tank was towed to a depot and the platoon continued operating with reduced strength. Richter's analysis showed that the average American tank battalion maintained 85% of its authorized strength in operational tanks throughout sustained combat operations. The average German Panzer battalion maintained 55% operational strength. The 30% difference translated directly to combat power. An American battalion with 53 authorized tanks would field 45 operational tanks. A German battalion with 53 authorized Panthers would field 29 operational tanks. In a direct engagement between these battalions, the Americans would have a numerical advantage of roughly 3-2 before considering tactical factors. Add in the Sherman's maintenance advantages, reverse speed, and more reliable turret traverse, and the engagement could easily favor the Americans, despite the Panthers' superior armor and gun. This was not theoretical analysis. These ratios appeared in actual combat records from France, Belgium, and Western Germany. American armored divisions with numerically inferior tanks consistently defeated German panzer divisions because they kept more tanks operational and employed them more aggressively. Richter's report included a section on track maintenance that illustrated the cumulative effects of design choices. Sherman tracks were single-pin design, meaning each track link was held by a single pin that could be driven out with a hammer and punch. Replacing a damaged track section required removing the damaged links, inserting new links, and driving in new pins. A trained crew could replace 6 track links in under 2 hours using only hand tools. Panther tracks were more complex. Each link was held by pins that required special tools to remove. The tracks were also heavier, requiring more effort to maneuver during replacement. Replacing damaged track sections on a Panther typically required 4 to 6 hours and specialized tools that were not always available at the front. More significantly, Panther tracks wore out faster. The overlapping road wheel design meant that the tracks bore more friction points than Sherman tracks. Panthers threw tracks more frequently, especially when making sharp turns on hard surfaces. The combination of faster wear, more frequent failure, and longer repair time meant that track maintenance consumed enormous amounts of time for Panther crews. An American tank company with 14 Sherman tanks might experience 1 thrown track per week during active operations. The repair took 2 hours. Total maintenance burden, 2 hours per week for the entire company. A German Panzer company with 14 Panthers might experience 3 to 4 thrown tracks per week. Each repair took 4 to 6 hours. Total maintenance burden, 12 to 24 hours per week. That time came from crew rest periods, tactical repositioning time, or maintenance time that should have been spent on other systems. The cumulative effect over months of operations was exhaustion. Panther crews spent more time maintaining their tanks than fighting them. Sherman crews spent more time fighting. Richter interviewed a Panther driver named Feldwebel Otto Kraus, who had served in France from June through August 1944. Kraus estimated he spent 4 to 6 hours per day on maintenance every morning required checking and adjusting track tension, inspecting road wheels for damage, clearing mud and debris from the suspension, checking fluid levels, and testing the transmission. Every evening required similar checks, plus refueling, rearming, and addressing any damage from the day's combat. When the Panther threw a track, which happened approximately twice per week, Klaus and his crew spent half a day on repairs. When more serious mechanical problems developed, the tank was out of action for days. Klaus's Panther went through 3 transmissions in 10 weeks of combat. Each transmission failure required towing the tank to a depot, waiting for parts, and waiting for mechanics. The average downtime per transmission failure was 6 days. During those 10 weeks, Klaus's tank was operational for approximately 42 days and non-operational for 28 days, an availability rate of 60%, which was actually above average for Panthers in Normandy. Richter contrasted this with maintenance logs from a captured Sherman that had served in the same campaign. That Sherman had thrown tracks once in 10 weeks. The crew had replaced 1 set of bogies after hitting a mine. Total unscheduled maintenance downtime: 1 day. The Sherman's availability rate was over 90%. The difference between 60% and 90% availability was the difference between winning and losing campaigns. Armies that kept their tanks running could maintain offensive pressure, exploit breakthroughs, and respond to enemy movements. Armies that lost a third of their tanks to maintenance at any given time fought defensively and reactively. Richter's final conclusion was blunt. German tank design prioritized engineering excellence over operational effectiveness. The Panther was a better tank than the Sherman in every measurable technical category, except the ones that mattered most: maintainability, reliability, and operational availability. The report recommended that future German tank designs, if any, should prioritize simple, robust systems over sophisticated, complex systems. It recommended standardizing components across vehicle types. It recommended designing for field maintenance rather than depot maintenance. It recommended that German engineers study American design philosophy and learn from it. The recommendations were never implemented. Germany surrendered 8 weeks after Richter submitted his report. The Waffenamt was dissolved. The engineers scattered. Some went to work for the Americans, some went to work for the Soviets, some went home and never worked in defense industries again. But the lessons Richter documented survived. After the war, American tank designers continued to prioritize maintainability and operational availability. The M46 Patton, M47, M48, and M60 tanks all featured modular components, standardized parts, and easy field maintenance. The M1 Abrams, introduced in the 1980s, could have its entire power pack engine and transmission removed and replaced in under 30 minutes using a specialized lift system. Soviet designers, many of whom had studied captured German and American tanks, adopted American maintenance concepts while retaining German armor protection schemes. The T-54 and T-55 tanks featured engines that could be removed in under 4 hours, transmissions that could be accessed separately, and standardized components that facilitated field repairs. The Soviet Vi-54 diesel engine used in the T-54 was designed with the same modular philosophy as American engines. It could be pulled from the tank, replaced, and the tank returned to service in a single morning. German engineering excellence had created magnificent tanks that could not be kept running in combat conditions. American engineering pragmatism had created adequate tanks that stayed operational through brutal attrition warfare. In the final accounting, availability defeated capability. The side that could keep more tanks running won the war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.